Hi, good day. This is Raghava Kashyapa, CEO of Qualitas Technologies, and today I'm very excited to share with you something unique that we've built. So, as you know, Qualitas Technologies is a solution provider that specializes in machine vision and AI, and we use computer vision and AI to solve complex applications when it comes to manufacturing quality control. So I'm really excited to share with you one such machine we've built, because one of the things that we do is we take challenging projects which are unique, difficult, and then we apply engineering principles right from image acquisition all the way to image processing using AI. So a machine vision solution requires images, right? So you need to capture images first, and that's where image acquisition comes in. And then you have image processing, which takes those images and processes them using software to come up with some kind of decision or some judgment on that images. So let's take a look at one example that we have developed. So to help me explain this particular machine, I'm going to bring in a colleague. So hi Vignesh.
Hi Raghav, thanks for that introduction. I am Vignesh Suvarna. I am working as applications engineer here in Qualitas. I'm responsible for end-to-end execution of machine vision related projects. Today I'll be explaining this machine and how the solution was developed for this particular use case.
Okay Vignesh, so thanks. So what are you holding in your hand? What is this?
So this is basically, most of us might not be knowing, this is a fiber optic spool, and this is a fiber which is used for our telecommunication purpose. So most of our data transmits to this one.
Got it. So this is a fiber optic.
Correct.
And it's wound in a spool, and there's a bunch. So how many, what's the length of a typical spool? How many kilometers do we?
Typically a spool varies from 2.1 kilometers to 52 kilometers or sometimes up to 70 kilometers as well. But this particular spool is somewhere around 32 kilometers.
32 kilometers. Yeah. So this is housing 32 kilometers of fiber carrying. So I would imagine that its quality is a pretty important factor. So what are some of the defects that we need to identify here?
So in this particular use case, we have two parts in this fiber optic spool. One is the flange itself, on which the fiber is wound, and the fiber. So we are inspecting for two regions. One is the flange and the fiber, as I told you. And in fiber, we have multiple defects, such as these dust particles, which we can see. These are the undesired dust particles, which should not be present in this fiber optic spool. And also we can observe there are some loose fibers. So these are also not recommended. And along with that, we can observe that there is some bump in the winding.
Okay, so it's not evenly wound.
Yeah, it's not evenly wound.
Okay.
So basically, when it's unwound, that might lead to some problem or some damage. So that is highly undesirable.
Okay, and on
also,
the flange?
On the flange, basically there are defects such as the scratch. As you can see, there are some observable scratches here. The residue of the previous, basically these spools are recycled, and the residue of the previous stickers are also deposited here, which can attract dust. So this is also undesirable. So we have to inspect for this one as well. Along with that, if there is any manufacturing defect or any damage that is caused, in the transportation or something, then we have to identify that as well.
Got it. So as you can see, the challenge with a complex part like this involves viewing the part across multiple angles. We have the flanges on the side. We have the uneven winding, which requires you to look at the entire spool surface at maybe two different angles. Then we have particles on this across the 360 degree cylinder, which requires you to be inspected throughout this 360 degrees. And of course the outer side, they have two sides of the flange. So there's also different colored spools, different designs. So it's not only having different lengths, but it looks like there's different colors, and there's also different flange colors, right? So the system has to adapt to all those different color combinations along with the variation in the lengths.
So there is lengthwise variation and also in terms of color.
Variation.
There is a huge variation.
So let's pick up one of these.
You can pick up any one of those.
And then I take this and then I place it on the machine.
Yeah.
All right, simple
you
enough.
Just have to simply press the
and
button.
I got to hit the green button. So here it is, looks like it's rotating and indexing it. How many positions are there?
Typically it indexes 24 times. At every indexing we are covering 15 degree.
15 degrees, okay. So 24 into 15 is 360.
It becomes 360 degrees, so there is no blind spot in that case.
All right, so now, we have 3 cameras on the top and then 2 on the side. So, I assume these 3 cameras are looking at for the dust?
The 3 cameras from the top will be covering the fiber as such. If there is any dust or any particles that might come over here. And these 2 cameras are looking at the flange and also the fiber. If there is any loose fiber that might come here, that can cause because typically the issue comes near the flange itself. Most of the defect comes near flange. So these 2 cameras will be looking at both the flanges.
So you're kind of zooming in on the flange edge,
correct,
the spool edge, and then that helps you capture any loose ends as well as any unevenness in the
correct
flange, so in the spool. Right? Okay, so and you see 2 cameras from the sides, one that's looking on either side of the. So there's one on the right hand side, and then there's one more on this on the left, which is looking at the 2 flanges. Am I right? Great. Okay. So, Vignesh, how small are these defects?
So the smallest defect size is 100 microns. We have to capture dust even if it's of 100 microns of size. And
100 microns. Okay. So 100 microns, and so that is pretty small. So we need to capture a large resolution image. So what are the resolution of the cameras?
Just to capture the image of the fiber and the flange, internal part of this thing, we are using 5 20MP camera along with the 112MP camera from the back side.
Oh, there's one more camera in the back.
One more camera in the back.
So let's look at that. So what is this camera?
So basically,
capture?
During the winding, there are chances that there might be uneven winding. When you touch it, you can feel that.
Yeah. Okay. So it's looking at the edge of the spool so that it's identifying any unevenness in the.
It's very difficult to be identified with the conventional method. So what we are doing is we are finding the profile by using a backlight. So by referring to the backlight, we can identify
you see the
profile.
shadow. Got it. So there's a backlight which gives you only the profile of this edge, and you can see the edge pretty sharply, and then if there's any
deviation in the.
So if it's not a straight line,
we can identify that.
We can look at there's any deviations. Okay, great. So seems pretty simple enough. So now let's look at how the process works. So to be able to identify any kind of defects, the first thing that you have to do is collect enough images. So an AI-based system is to capture enough images that allows you to train an AI model. So the first step in any image acquisition is data collection, right? So how are we doing data collection here?
So we have built a specific app for that purpose itself. We call it the data collection app. So this is a data collection UI. This is how it looks.
So can I start?
Yeah, I can press that button.
All right. So I'm going to start the cycle.
So since we are just doing the data collection, this is an entirely different program that we are switching. So we are switching the program via PC itself. But we are just collecting all the images at a shot. This button is just to collect all the images. It will come in the data collection UI.
Okay, but it's not turning?
No, while data collection it will not turn. Only in the inferencing it is automatic process. Data collection we need some specific defects to be captured, right? So
okay, so this is the spool edge. Okay, so you can see
here we can see the profile. There are
okay, so just to be clear, this is the light.
Yeah, this is the backlight.
And this is the actual spool. So you can see the profile of the sides. Correct. So that's the top camera that's behind.
Correct.
And then the 3 cameras which are taking images off the spool.
Yeah,
so this is on the side
cameras.
So is it possible to zoom in? Yeah. So you can see. Can you see the defects on this? Does it have any defects?
This is one of the defects. We can see a white region, right?
Okay.
So this is one of the defects. This is caused due to physical pressure. It's a plastic part.
Yeah, this is the defect. How about the
and
spool?
Also this is a defect region.
That's a defect. Okay.
Yeah. Close this.
Okay, and this is the other side.
Yeah, this is the other side.
Yeah, you can see there
are some defects here. You can see the defects here. This is a glue residue.
The glue residue.
Not desirable.
Okay.
And the top camera. This is how individual fiber looks. This doesn't have much of a dust or something. But
so this okay. Is there any?
No, this one doesn't have much.
This doesn't have any dust. Okay. Can we look at the other one? So this is a good sample.
Yeah, it's a good sample.
Got it. So then once you capture these, what are you doing here? So
after we have 8 different cameras that are capturing images. After that, we will see individual defect. Individually the operator has to see
each individual. So the operator looks at each individual image and then identifies whether they're good or bad.
Correct.
And if it's bad,
he has to classify it.
You have to select what particular defect it is. So if it has a dust, if it's actually good, if it has a loose winding, a scratch, or if he's confused.
Yeah, if he's
he
confused,
can also
he can
say
select
that.
this one.
Okay. And then once you do that?
Yeah, once he does that, for example, this is a good
sample,
good fiber.
okay.
So I'm selecting as good. Then he has to just select, do it for all the images.
But this has the glue residue on the side, right?
For example, this has a glue residue.
Yeah. Also, you do it for every image.
Individual image we have
for
to
every
do
image, okay.
Because this will be used for training.
Yeah. So each image you have to annotate.
Yeah. If, for example, this one has some black marks, we are selecting as black mark. And after that, we have to just save the checked images.
So once these images are captured and then a judgment is found, so the images are then sent to a PC. The PC is in the back here, right? So let's take a look at that PC if you can see that. So this is, okay, so that's the PC in the back, and that's basically inferencing the images that are taken from these cameras. And then so the output of the PC, what happens? So if a defect is found, what happens?
So once the PC, when an inferencing UI gives us an output as it is defective, the output is given to the PLC. So from the PLC, it will be it will be showing in the
okay. So there is a visual output. It flashes red, and then
along with a beep.
Along with the beep, and then the operator knows that this is a defective sample, and he keeps it.
He can send
aside.
it for rework.
Got it. Great. Thank you, Vignesh.
Thank you.